Yes, sir.
Are you able to hear me properly?
Yes, sir. You are clear.
My slide is visible to you, no?
Yes, sir. It is visible.
Okay, just today we are going to discuss this natural convection problem. A fluid with a density rho and viscosity mu is located between two vertical walls at a distance 2b apart as shown in figure. The length and width of the wall is very tall as compared to distance between them. System is enclosed from all the sides. So this system is not open. Okay, this is actually, you can think of a rectangular box. Okay, rectangular box, and this length here it is given, the length and width is very large as compared to distance between these two parallel plates. And it is enclosed from this side, it is enclosed from front side, back side, top side, right side, left side. So it is kind of cuboid, not cube, a cuboid, rectangular cube, you can say. So rectangular cube is there, enclosed from all the sides. The heated wall is maintained at temperature, higher temperature T2, and the cooled wall is maintained at temperature T1. Derive the equation for temperature profile and velocity profile and explain how velocity profile will change if we assume that a temperature difference is sufficiently smaller, because this, okay, if delta T is smaller, then what will be the velocity profile? Discuss the relationship between density and coefficient of volume expansion, give the physical significance of Grashof number. Okay, so Grashof number, when we will convert velocity profile equation into dimensionless form, so you will get a Grashof number. So you need to discuss the physical significance of Grashof number. Just take out all the information. Roll number 5, Aditya. Roll number 5, Aditya.
Yes,
are you able to?
Yes, sir.
Are you
Yes,
able
sir.
to hear me? Initially,
Yes, sir.
I heard your name almost
Sir,
4-5 times.
yes, sir. Initially, the network was fluctuating. I couldn't hear which roll number you were calling out. Sorry, sir, about that.
Okay. So can you just explain what is the given information in a problem? Can you see a PPT? Can you
Sir,
read?
it's still fluctuating. So
So you
just a
are not
second.
able to see the PPT?
No, sir, just a second. The network is not. It's not proper, sir.
Okay.
I'm seeing a blank screen.
Okay, from next class onwards, we will have offline classes. How many people are there? Roll number 88, you just update me regarding all the people present in a campus after the class. You inform me everything about all who all are available in a class and how many. Any classes is started? Number 88 is there.
Yes, sir. Sir, so far, no offline class. It is going in hybrid mode only. Like
Hybrid
today,
mode. Who is taking hybrid mode?
Sachin sir will call us today in the department for interacting with the students who are present on campus, and the class will go online.
Okay. At what time that hybrid class is there?
It will be at 2 o'clock.
2 o'clock. You just update me, okay, about everything.
Okay.
How many people are there in a campus?
Sir, after Sachin sir's class, it will be quite clear that how many students are here. So I'll count in the class and then inform you.
Okay. So most probably from next class onward, we will be starting offline classes. That depends upon what is the input from this Pritesh after the afternoon your hybrid class and all. So yeah, Aditya, roll number 5, Aditya. Aditya Khatu.
Yes, sir. Yes, sir.
Yeah, can you just take out all the information from the slide?
Yes, sir. We have density rho of the fluid, viscosity mu. There's 2b distance between the two plates.
Yeah, this 2b is very small as compared to a length. First of all, length and width
Yes,
is
sir.
perpendicular to this screen. Width is
Yes, sir.
perpendicular to this skin. This 2b is
Yes, sir.
small. This is a rectangular box. Okay, this is a rectangular box enclosed from all the sides.
Yes, sir.
This is not a free flowing fluid coming in and going out. So this is a rectangular box. So this top is closed, bottom is closed, front is closed, back is closed. This left hand side is kept at temperature, lower temperature. Right hand side is kept at a higher temperature. So higher temperature, lower maintained at T1. T2 is a higher temperature. T1 is a lower temperature. Okay. So what is expected now? Here we want a velocity profile and temperature profile. So Aditya, roll number 5. What is your
Yes, sir.
expectation? Whether velocity will have effect on temperature profile or temperature profile will have dominating effect on velocity profile? Why there will be a flow? Why there will be a velocity? Why there will be a temperature variation?
Sir. So could you repeat the question?
So why there will be a temperature variation? Why there will be a velocity miss? You can say momentum will be there. Velocity, why there will be a movement of the molecules and why there will be a temperature variation? First of all, why?
Because of the heated plate and the cooled plate, sir. There's a temperature difference because of the gradient. There will be.
Okay, because of this.
Yes, sir.
Here, this is heated plate, this is cold plate, so there will be temperature variation. And why
Yes,
there will be a velocity? Why there are a movement of molecule? Because this is enclosed. Whether molecules will move?
Sir, yes, sir. So due to the movement of the particles, sir.
Yeah, why molecules will move? Why
So because of the temperature difference.
What is the responsible? Why if there is a temperature variation, what will change? Why there will be a velocity, moment of molecule? Because of temperature variation,
Yes,
there
sir.
will be
Yes, sir.
moment of
Yes, sir.
molecule.
Yes.
Because of temperature variation.
Yes, sir.
So can you give me an example? If there is a temperature variation, there will be a moment of molecule. So anywhere
Sir,
that
in conduction, sir.
conduction, molecules will move in conduction.
So particles will have slight movement in conduction.
But that cannot
But
be
they're not.
given
Yes,
rise
sir.
to a velocity, bulk motion. Velocity is
Yes,
calculated
sir.
and this fluid is filled actually. Fluid, it is either gas or liquid. So you can assume either gas or liquid. Fluid is filled in between these solid plates. So solid plates from all the sides. Here roll number 6, Aksh.
Yes, sir. The same question.
What might be the reason?
So actually the thing would be like as the temperature is increasing, the kinetic energy of the particles would increase. So they would have movement, just like in convection, like if the water is boiling, so the particle moves up.
Yeah, kinetic energy will increase because of which force?
And because sorry, sir, I couldn't understand your question.
Because of which force kinetic energy will increase?
So force, like sir, temperature is the driving force there. So like the temperature, so internal
Temperature
kinetic
cannot be a
energy.
driving force for velocity, na?
Yes, sir, that is right.
Some gradient in force. Potential gradient is the gradient for velocity. Because of temperature gradient, there will be a potential gradient. What is that potential gradient is called as? Which force? Roll number 8, Ali.
Yes, sir.
Yeah. So you might have seen a hot water. If you have a cup of hot water will be try to be at top and cold water will be try to be at bottom. What is the force which is giving rise to this kind of phenomena? Ali?
Sir, potential energy.
Potential.
Sir, lower density.
Yeah, lower density. Yeah, density the difference in density, which kind of forces will act on? Then if there is a difference in density, yeah, Nitin?
Hello, sir.
Tell me. Difference in density, which kind of forces will be get because of difference in density?
Sir, gravity force.
Gravity force. And more precisely, why this lighter molecule will be at top and heavier molecule will be at the bottom?
Sir, due to mass, density and mass.
Buoyancy. It is called as buoyancy. Yeah. So, so if I read out a whole book, now still you people will not give the very precise answer because of there is a temperature difference. There will be buoyancy force. Okay, buoyancy force. Because of temperature difference, buoyancy force will be there, and because of buoyancy force there is a flow. So certainly velocity will have more effect of temperature as compared to temperature being an effect of velocity. So velocity depends on temperature variation as compared to temperature depends upon velocity. Okay. So here we need to solve this problem first, a heat transfer, then a momentum transfer, because velocity depends upon temperature more as compared to temperature depends upon velocity. Okay, velocity, temperature has less because here heated plate is there, here cold plate is there, and because of buoyancy, I am expecting that flow will be in upward direction, and that flow will be very slow because these boundaries are closed. Flow will be very slow, so certainly that velocity will not have much effect on temperature. So temperature, velocity have more effect of temperature as compared to temperature having an effect of velocity. That is why first we'll go for heat transfer and then we'll go for a momentum transfer, solving the problem how to get a temperature profile and velocity profile. So this is the problem. So what will be the expected temperature profile? Rule number 10, Aman.
Yes, sir.
Expected temperature profile.
And the heated wall is heated wall is maintained at T2, so it will be higher temperature, and cold wall is at the temperature T1.
Yeah, so here I will have higher temperature, here I will have lower temperature, and
Yes.
I can expect a linear variation.
Yes.
I can expect a linear variation and neglect what I am neglecting, a convective flux in z direction, because there will be a moment of molecules in z direction because of buoyancy force. Because of buoyancy force, there will be moment of molecule. Velocity will be in z direction, but that convective flux will be smaller as compared to conductive flux in this case. Okay, this will not be case in general. Generally, whenever there is a convection and conduction is there, convection will be dominated by conduction. But here, as all this system is enclosed from all the sides, and moreover, there is a temperature gradient only in one side. So conduction in y direction is dominated as compared to convection in z direction. Molecules are moving, but moment of molecule is very small, because this moment, why there is a moment of molecule? Because of the buoyancy force. Because of the buoyancy force, there is a moment of molecule. Hence, there is no other potential gradient which is giving rise to velocity. Only buoyancy force is the force which is responsible for the velocity. That is one reason why we will have very slow velocity. And secondly, this container is enclosed from all the sides. Container is enclosed from all the sides. So convective flux in z direction is negligible as compared to conductive flux in y direction. So if this plate is kept at temperature T1, this plate is kept at temperature T2. So certainly I can expect there will be some linear variation. If I consider a convective flux in z direction also, so this is my y direction. This is my y direction, this is my z direction. If I consider a convective flux in z direction, then there will be non-linearity. Non-linearity in this curve, some S kind of curve I can expect actually. Some S kind of curve I can expect here actually. But at the middle point, there will be average temperature. Here I will have T2, here I will have T1. Some non-linear if I consider a convective flux in Z direction, but it is very logical to neglect this. To simplify the problem, we can neglect the convective flux in Z direction because velocity is because of buoyancy force. That is one reason why there will be very small magnitude of velocity in Z direction. Secondly, a container is enclosed from all the sides. Because of these two reasons, the velocity, magnitude of the velocity will be very, very small. Magnitude of velocity will be very, very small. So we can neglect that convective flux over conductive flux. As there is a conductive flux, so we can have this linear variation and problem will be very easier. We are just considering heat transfer from this plate to this plate only, neglecting a convective flux in Z direction. To this step. So the temperature is varying only in y direction. You can take a differential thickness in y direction. Use a combined energy flux. So this is the combined energy flux E for y direction. So velocity in y direction is 0, 0 because there is only velocity in Z direction, Vz, neglecting end effects. At the wall, there will be a velocity in y direction, x direction, every direction will be there. That neglecting end effects, we can assume that velocity in y direction is 0. This will be 0 at velocity in y direction is 0. So Ey will be equals to just purely conduction. So you can see this is tau y is dvz by dy. So there is no change in a velocity in y direction. Okay. So because of that, that can be negligible. Okay, negligible variation. So because you can see the first of all, this velocity, magnitude of velocity is very, very small because of this buoyancy, and hence I can neglect this also. Neglecting this, so Ey will be equals to just purely conduction in y direction. So and this Qy is given by Fourier law of heat conduction using shell balance approach. So this will be a dq by dy equals to 0 minus k dt by dy equals to 0 using these two boundary condition. At y equals to minus b, temperature is T2. At y equals to plus b, temperature is T1. So this is neglected convective flux. Okay, this is, you can say this is not a convective flux. This is actually a kind of a viscous heating. Viscous heating can be neglected when velocities are small. For viscous heating, either I should have very large value of viscosity and large value of velocity. Then there you can have some viscous heating. So you can think of a fluid layer rubbing to each other, and generating the heat. That is kind of a viscous dissipation. That will be more if magnitude of velocities are more and magnitude of viscosities are more. Here velocities are very, very small, hence we can neglect this also, and it will be purely a conductive flux, and we are neglecting a convective flux in y direction, z direction. So substituting this, it will be solving for this. Which equation you will get? Can you solve for this? Integrate this twice and substitute this boundary condition, get the constant and get the temperature profile. Roll number 11, Chetan.
Yes, sir.
What will be the temperature profile then?
Sir, it will be linear.
It will be
Temperature
linear.
profile, na, sir.
What is the equation?
Sir, equation will be T is equal to C1y plus C2, and then we have to put this boundary conditions. Then
Why this is
it will
neglected?
become.
Chetan?
Why yes, sir.
Neglected? Can you see my
Sir,
curve?
viscosity. Sir, viscosity, viscous heating can be neglected.
Why? Very good.
Sir, sir,
Why
because means velocities are negligible, sir.
Very good, very good. Because here I am expecting small magnitude of velocity. Hence, this viscous heating are neglected. Why? So the Vy equals to 0. Why?
Sir, because means in y direction we are not considering convection, neglecting
But logical reasoning will be Vy equals to 0. Why? But because this is enclosed, at the top there will be velocity.
yes.
So why Vi equals to 0 here? We are considering. Which logic we can consider Vy equals to 0?
Sir, there is no flow in y direction.
Look, this is enclosed. Okay, this is enclosed.
Yes.
So I'm expecting that flow will be like this.
Yes, sir.
Because this is enclosed. This here fluid will get heated up.
Yes, sir.
Then it will have some buoyancy force. So it will lift the molecules will move here. Here there is no place to go up, so it will move here actually. Then because it will get pulled up and it will move down. So here
Yes, sir.
we have velocity in y direction, but we are neglecting that. Why?
It is very small.
It is in very small region actually, and length is larger. It is given that
Yes,
length
sir.
is larger, but that variation is only limited to some region, smaller length. Hence, that is called as a, how to interpret that? End effects are neglected.
Neglected, yes, sir.
The end effects
Because
are neglected. At the end, there might be a velocity in y direction. At the end, there might be a velocity in y direction, but we are not considering that. Considering that end effects are neglected, we are interested in fully developed flow here. Fully developed flow that we are interested in. Okay. So everybody got this temperature profile where T bar. What is T bar? T bar is the average temperature. T bar is the average temperature. If this is a center point, then it will be T1 plus T2 by 2. Okay. So T bar, delta T is T2 minus T1. Okay. And T bar is a half T1 plus T2. So check, everybody is getting this temperature profile. Roll number 12, Anand.
Yes, sir.
Did you got this temperature profile?
No, sir, I got like C1 equal to K delta T by 2V. So that I'm
Some people got the message in chat box. You can write in chat box. People are getting. Yeah, many people are getting. So this will be a temperature profile. T equals to T bar. T bar is the average temperature. Delta T is the temperature difference. T bar minus half delta T Y by B. So here you can see, you can put at y equals to minus b. If you substitute y equals to minus b, so it will be T bar plus delta T, half delta T, and you will get T2. Substitute these values here, and y equals to plus b, you will get temperature equals to T1. So expected, this is expected temperature. And what are the assumptions? Basic assumptions are, first of all, end effects are neglected. Viscous heating is neglected, and secondly, convection in z direction is negligible. Convective heat transfer in z direction is negligible as compared to conductive heat transfer in y direction. This is what assumptions are there. With this assumption, you can add this also, because there is a velocity in z direction. So there will be convection in z direction. So there will be conduction in y direction and convection in z direction. So all together will give me a temperature variation. Okay, all together will give me a temperature variation. So that we are neglecting, because expecting that this velocity in z direction is because of buoyancy force. First reason. Second reason is it is enclosed in a rectangular box. Whole flow is enclosed in a rectangular box. So velocity magnitude of velocity will be smaller. Hence, we are assuming that conduction will be dominated over convection. This is very special case. This is very special case. Otherwise, in general, whenever there is an open system and convection is there, convection will be dominated by conduction. Convection will be more and dominating mode of heat transfer over a conduction most of the time when you have open system, or most of the time. Here, because it is a closed system and buoyancy is the only driving force for velocity, these are the two reasons why we are expecting there will be a lower velocity. Lower velocity means lower convective flux. Velocity will be characterized by the convective flux will be the characterized by velocity. So that is why we can expect that conduction will be dominating over convection actually. This is clear to everybody? Here, roll number 12, Anand. What
Yes,
is this
sir.
equation?
Yes, sir.
Have you derived the equation?
Yes, sir.
Can you show me your notebook?
Yes. What?
Okay, nice. So, and thereafter now temperature profile we got. Now we will move on to velocity profile actually. Now we will move on to velocity profile. What will be the expected velocity profile? Roll number 14, Anmol.
Yes, sir.
What
Sir,
is the expected velocity profile?
as
Fully
the
developed.
okay, sir. Sir, as the whole fluid is enclosed in a box, sir, so from fluid from one side will be going up, and fluid from one side will be going down to,
Okay.
and the velocities at the surfaces will be equal to 0 because no slip boundary condition.
Very good.
And the maximum of one side in each side, like lying between the middle and one of the plates, in between somewhere will lie the maximum of each velocity,
Very
each
good.
gradient, and there will also lie a 0 point in the middle, sir.
Yeah. Why? Because this here I will have negative velocity, here I will have positive velocity.
Yes, sir.
So somewhere there will be 0 velocity. This is what expected velocity profile is. So certainly this velocity is 0 here. Okay, this velocity is 0 here. This velocity is 0 here because of no slip boundary condition. So velocity is 0 here because of no slip boundary condition. Velocity 0 is there because of no slip boundary condition. And I am expecting, as here temperature will be higher, as in this region temperature is higher, this fluid will try to move up. This fluid will try to move up, and here temperature is lower, this fluid will try to move down. So this I can take it, if say this is my z direction, this will be a positive Vz and this will be negative Vz. So at the center point there will be a 0 velocity. And net mass flux over the cross section, that will be also equals to 0. Because if I consider a mass flow rate from here to here and here to here, so overall mass flux at any cross section, that will be equals to 0, because this will be a positive mass flux, this will be a mass flux in negative direction. So net mass flux over minus b to plus b will be equals to 0. Okay, this will be the expected velocity profile. Now, how to get a velocity profile? Number 15, Sai.
Hello, sir.
How to get a velocity profile?
Sir, we can use equation of motion in Cartesian coordinates.
Equation of change or shell balance. Shell balance for momentum transfer. Which velocity? Which momentum equation we will be using? X momentum, because this is a rectangular box, so we will be using
Cartesian coordinates.
Cartesian coordinate system. So we have X momentum, Y momentum, and Z momentum. So which momentum we will be using? Which momentum?
Sir, Z momentum.
Z momentum. So whether Vz is varying with XYZ, in which direction Vz will be varying?
Sir, y direction, sir.
Why it is not varying in X direction and Z direction?
Sir, Z direction it will be constant due to it is a continued, I mean, it's a closed boundary conditions. Continuity equation.
Not continuity, not continuity. This will not. It is
In
not
Z
varying in
direction,
Z
sir.
direction because it is enclosed and
Yes, sir.
and why we can neglect variation in Z direction? End effects are neglected.
Yes, sir.
Okay, end effects are neglected. And why it is why we are yeah.
Hello, sir.
Why we are neglecting a variation of Vz velocity in X direction?
Sir, X direction because it is very I mean, its width is very high than.
And hence
Its width is very high, sir.
And hence we can neglect the variation in. So reason is end effects are neglected.
Yes, sir. Yes, sir.
Okay, that you should add because length is very large and neglecting end effects. Okay. So we need to take a shell momentum balance or equation of change. Okay. So this is X momentum, X equation of motion, Y equation of motion, Z equation of motion, and we are discussing with a constant viscosity system. Constant viscosity system. So we can use Navier-Stokes equation also, Z equation of motion. So this is Z equation of motion. So now this is Z equation. Velocity is not varying with the time. Steady state. We are considering steady state. Hence, this is equals to 0. Vx equals to 0 or velocity is not varying in X direction. End effects are neglected. Velocity is varying in Y direction, but Vy equals to 0. There is no velocity in Y direction. So this is equals to 0. Okay, this is equals to 0. And then velocity is not varying in Z direction because end effects are neglected. So del P by del Z is non-zero because of that only. So this is because of buoyancy force. This is because of buoyancy force. Okay, this will be non-zero. And mu, the variation Vz is not varying in X direction. End effects are neglected. Vz is varying in Y direction. Vz is not varying in Z direction because end effects are neglected. So this is 0. 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 This is everything is 0. Non-zero term is 1. This is 1, 2, second non-zero term and third non-zero. So these are the non-zero terms actually. Now you can see buoyancy force. So buoyancy force is associated with a change in a density. Why buoyancy force exists? Because there is a gradient of density. So this density is not constant. This density is not constant. Hence, it is giving rise to pressure gradient. Hence, it is giving rise to a velocity in velocity in Z direction. Hence, it is responsible for Z direction. This gradient of density, because of variation in temperature, density is changing. So, what is the equation which we can use? So, density and temperature correlation. So, we can use from thermodynamics. Okay, we can use from thermodynamics a variation of density. This is density. So density can be estimated by using a density at average temperature. Okay, density. This is a simple. You can think of this some arithmetic equation. Arithmetic equation when you want to estimate the property using the property of nearby points. So this is the density at average temperature plus variation of density at average temperature del rho by del t minus t bar plus del 2 rho by del t square t minus t bar square and so on. This is which expansion? What is the name of this expansion? Have you heard of this expansion anywhere in mathematics? Roll number 17, Leshma. Roll number 17. Roll number 17. Roll number 17. 18, Ashish?
Yes, sir. Hello.
Yeah. This kind of expansion, have you used anywhere in mathematics or thermodynamics?
Sir, Taylor series, sir.
Yeah, Taylor series expansion, exactly. This is Taylor series expansion. Simple mathematics also will give me a property at nearby point using the property at nearby point. So T bar, and this T is equals to T bar. Then in terms of T bar, this rho can be interpreted in terms of density at T bar. So this is the Taylor series expansion, and neglecting all higher order terms. This neglecting all higher order terms means T minus T bar. This is true for T minus T bar, smaller value of T minus T bar. If T minus T bar is smaller, if T minus T bar is smaller, T minus T bar square will be even smaller, T minus T bar cube will be even smaller. Hence, all higher order terms can be neglected. Moreover, this del rho by del T, okay, this is a compressibility factor. This is compressibility factor. This will be equals to average density. It will be average density multiplied by beta bar T minus T bar. And what is beta? Beta is 1 upon V del V by del T at constant pressure. And this is a specific volume, 1 upon rho. This will be minus 1 upon rho del rho by del T, where average this is average density, and this will be a coefficient of volume expansion. This is coefficient of volume expansion. Why we are doing all this? Because this velocity, why we are getting a velocity? Because of buoyancy force. And how to encounter, how to consider, or how to account for this buoyancy force? Buoyancy force is here, variation in density. Variation in density will give rise to a buoyancy force. That is why we are getting this this thing actually, variation in pressure. Because of buoyancy force, we are getting variation in pressure, and all together will give me a velocity in z direction. And it can be associated with the coefficient of volume expansion. This is compressibility, and this is the volume expansion. In terms of volume expansion, you can go in thermodynamics, okay? And d rho by dt, compressibility and this volume expansion can be correlated with each other. 1 upon rho d rho by dt at constant pressure. Now substituting it here actually, and this is average. This I can calculate at average temperature, this density at average temperature, density at average, this coefficient of volume expansion at average temperature. So substituting this in this equation, now I can integrate this equation. Integrating this equation, I will get a velocity profile. Integrate this equation and use this boundary condition and use the temperature profile. T is average temperature minus half delta T y by B. This temperature is also function of y. Okay, substitute this temperature here, and this is the variation of density using coefficient of volume expansion beta, and substitute this here, integrate this equation, and this is rearrangement. So this you can take it as a constant, del p by del z as it is. Okay, rearranging this equation and integrating this equation and considering taking out the boundary condition, y equals to minus beta, vz equals to 0, y equals to plus b, vz equals to 0. These are no slip boundary conditions. Substituting this, so you should be getting the velocity profile. Get the velocity profile of this nature actually. So integrate this equation twice. So you will be getting two constant. Get the value of constant C1 and C2. Rearrange the equation in this form. One bracket will be y minus b cube minus y minus b, plus another bracket will be y minus b square minus 1. So what will be constant term here? Constant. So get the value of C1 and C2 and rearrange the equation to get the velocity profile. Roll number 18, Ashish.
Yes, sir.
Are you getting what is going in class?
Sir, I am integrating that part.
Huh?
Sir, I am doing the integration part.
What?
Hello, sir.
Huh? Tell me.
So I'm doing that integration part, like if we said
You are following, no? You are following what is going on in class. Because this problem is very, very simple as compared to whatever previously we have solved very complicated problem, complicated mathematics. So boundary conditions are also very simple. Mostly boundary condition, temperature is given at the surface. And so only the thing is when you need to integrate this equation twice and substitute this boundary condition, get the value of C1 and C2, substitute the value of C1 and C2 and rearrange the equation. So this constant value is rho bar, average density, G, acceleration due to gravity, average coefficient of volume expansion, temperature difference, V is the difference between these two plates, V square divided by 12 mu. Mu is the viscosity of the fluid, the viscosity of the fluid, multiplied by y minus b cube minus y minus b plus P is the difference between two plates, hot plate and cold plate, divided by 2 mu, del P by del Z plus rho G. This is constant. This is treated as constant. So that multiplied by whole bracket is y minus b whole square minus 1. So anybody is getting this after rearrangement C1 and C2? So anybody getting this equation? Yeah, Ashish.
Sir, I'm stuck in.
Not got the equation. Just try for it. Very easy actually. Integrate this equation twice. Here
Sir,
you will get first y. Here you will get y square by 2 plus c1, and again integrate it by again integrate. Then here you will get y square by 2. Here y cube by 3 and so on. Then one more constant c1 y plus c2. And substitute this boundary condition at y equals to minus b, velocity is 0, y equals to plus b, velocity is 0. And then you should be able to get this. Anybody got this equation? So you can write in chat box if you are getting this equation. Yeah. Aditya got. Aditya, everything is correct? The equation? Row number 60, Aditya.
Yes, sir.
Yeah, you got the equation, na?
Yes, sir. I got the equation.
Okay, very good. So now here, this is the overall velocity profile. Now we can simplify this velocity profile. Okay, you can simplify this velocity profile for 3 additional assumptions. Okay, 3 additional assumptions. Not 3, only you can say if delta t is very, very small and neglecting the value with the delta t square. If delta t is smaller, so neglecting the value with the delta t square, this del p by del z will be equals to minus rho g. Okay, so this is what we are. So net mass flow rate in z direction. If we consider with a delta t smaller value and neglecting delta t square, this will be a net mass flow rate. Okay, so you can think of velocity multiplied by cross sectional area. So this will be in b direction, and you can consider x direction. Anyway, x direction velocity is constant, so you can neglect. This will be a net mass flow rate in z direction per unit width. What is this? This will be a net mass flow rate in z direction. So even if you consider that width or neglected that width, that doesn't matter. Velocity multiplied by cross sectional area. This will be dy into w, width. Width is constant. Okay. So this will be volumetric flow rate multiplied by density. That will be a net mass flow rate in z direction per unit width. Okay, per unit width. And this density, writing the density, variation of density in terms of how it is changing with the temperature using average density and coefficient of volume expansion. Coefficient of volume expansion, you can substitute it here, and this is the definition. This is the substituting the definition of temperature profile. How temperature is varying with respect to y. Okay, with respect to y, how temperature is varying, and neglecting all the terms with the delta t square. Neglecting all the terms with the delta t square. So using this fundamental net mass flow rate in z direction, this will be equals to 0, because whatever be the fluid going up will come down. That already at any cross sectional area, net mass flow rate in z direction will be 0, because whatever fluid is going up from one side, another side it will go down. At steady state, if I take a net mass flow rate, that will be equal to 0. And this is the density profile. You can say density profile, density variation with respect to temperature, and this is the temperature profile. Substituting it here, velocity profile, density profile, and temperature profile, and neglecting delta t square equals to 0. So what you will be getting? You will be getting del p by del z equals to minus rho bar g. So this is the outcome for this problem actually, and we can neglect this. Most importantly, this is the assumption. If delta t square is neglected, delta t is smaller, so delta t square will be even smaller, then I can neglect this. Delta t square is neglecting, so del p by del z will be equals to minus rho g. So this will be equals to 0. So I can neglect this, and this will be my velocity profile for delta t, smaller value of delta t. So now we'll try to get this value. So mathematically, you need to derive at home. Okay, this is the net mass flow rate in z direction per unit width. Rho into Vz into dy, integration from minus b to plus b, that equals to 0. And this is the density profile, this is the temperature profile, neglecting delta t square equals to 0. So how this can be 0? So you can see this is first of all, this is my velocity profile. What is this? This is my velocity profile, and this is my density profile. Density profile with a temperature. Density profile with a temperature. So this temperature is substituted here actually. Substituting temperature profile. This is velocity profile substituted, density profile substituted, and temperature profile is also substituted. This is this equation, same equation. This is density. So density rho into rho b, and this temperature profile is substituted. Rearranging this equation, this whole rho, this will be the density profile and temperature profile, and this is what my velocity profile into dy, and this is integration from 0 to b. Now for simplifying this equation, we'll assume this equals to some constant. You can see this is constant. This is constant, this is constant, this is constant, this is constant, everything is constant. Say this is equals to P. Again, everything is constant. Everything is constant. So this constant with respect to y. Okay, this is constant with respect to y. So this equals to Q, and say third constant is this. Okay, this is third constant, which is say R. This is just one mathematical arrangement. This is say P. This is say Q, and this is say R. So rearranging this equation, so P multiplied by Q term raised to 1 term plus q raised to square term minus 1 plus this rho bar r, this is r y by b dy. Now I can integrate this equation. Before integrating, I can split this bracket. So this rho multiplied by whole bracket and r into yb multiplied by whole bracket. This is the whole bracket. And then this will be a y by b is taken inside. Okay, y by is taken inside. And this will be a whole bracket rearranging where p equals to this complete term, q equals to this complete term, and r equals to this complete term. So wherever r is there. Now integrating this equation, this is the integration. Now you can see after integration, this is minus b to plus b. So certainly this is raised to 4 term and this is square term. This is raised to 4 raised to square minus b to plus b. This will be equals to 0 because minus b square will be equals to b square and plus b square equals to b square. So this is integrated from minus b to plus b. This is raised to 4 even. This is raised to square. So this is equals to 0. If I substitute the limits of integration, this is say non-zero, and this is again raised to square term and raised to 4 term and raised to square term minus b to plus b. This will be equals to 0. Now p into r. If we analyze p into r, so p into r. What is the p into r? This is my p and this is my r, which will be equals to delta t square. Here one delta t is there, here one delta t is there. So delta t square. So neglecting delta t square. So this will be neglecting delta t square. This will be equals to 0. Neglecting delta t square. This will be equals to 0. So because this is a even power, this is even power. Integrating from minus b to plus b, this will be 0. Both will be 0. So overall, this will be equals to 0. This integration will be only this will be equals to 0. So this is what the value of this integration. Everybody got this? Anybody has any problem? Now integrating this equation. Okay. Now substituting this limits of integration. This is substituting these limits of integration and rearranging the equation. So rearranging the equation. So what you will get? Now here you have substituted q and rho bar. Q and rho bar is substituted, and this is what equation we'll get. So this is everything is constant, which will give me del p by del z plus rho g equals to 0, and hence this you can see del p by del z equals to minus of rho g. Okay, del p by del z equals to minus of rho g. This is what our velocity profile was there for delta t square, neglecting delta t square. So I can eliminate this term and overall velocity profile will be this. This is simplified velocity profile with the assumption that neglecting delta t square. Okay, you go home and try to do all mathematical manipulation with all detailed steps. So why this is neglected? Because this is even power, this is also even power. Even power integrating from minus b to plus b will be 0. Again, why this is neglected? This is even power, this is even power. Minus b to plus b, even power will be equals to 0. Why this is neglected? This is PR. You can see this is PR. PR will be equals to delta t square, and this is whole constant. And neglecting the terms having delta t square, considering delta t smaller, delta t square will be even smaller. That neglecting that delta t square, this will be equals to 0. So net mass flow rate. So rearranging this equation, I will get this del p by del z equals to minus rho g. So this will be the velocity profile. Anybody has any problem in this? Now I can use a dimensionless number. This will average velocity. Average velocity of upward moving stream. Upward moving stream means minus b to 0. Minus b to 0 is upward moving stream, and 0 to plus b is the downward moving stream. Okay, so you can integrate this equation from minus b to 0. So this is, you can see. So what will be the average velocity from this point to this point? This will be minus b to 0. So integrate this equation from minus b to 0. That will be a velocity of upward, average velocity of upward moving string. So integrate this equation from minus b to 0 dy. So this will be an average velocity of upward moving string. So this is average velocity and this is velocity profile. So we can rearrange this equation in terms of dimensionless velocity. So say this is my dimensionless velocity, this is my dimensionless y, dimensionless width, and this is dimensionless velocity. So rearranging this equation, so this will be an average velocity equals to 1 upon 12 Grashof number y cube dimensionless distance minus y bar. Okay, y cube bar, y bar cube minus y bar, where Grashof number equals to rho bar square g beta delta t b cube divided by mu square. Delta t is T2 minus T1, and this is the definition how density is varying with the temperature, and delta rho. If I consider delta rho equals to rho 1 minus rho 2, so rho 1 minus rho 2, so rearranging this equation, so what I can write is Grashof number is rho g beta cube delta rho divided by mu square. And what is the physical significance of this Grashof number? It is the ratio of buoyancy force. So you can see this rho and g is representing buoyancy force to viscous force. So this is the ratio of buoyancy force to viscous force is the physical significance of Grashof number. So everything is clear to everybody? Just I will quickly go through all the slides. If you have any questions over any slides, just let me know. This is expected temperature profile when conduction, only conduction is considered. Solving for this is the temperature profile we will get. And then velocity profile. So this is expected velocity profile. Half will be moving upward, half will be moving downward. So you can get it from Z equation of motion with constant viscosity. Substituting all the assumptions, this is the equation. So integrating this equation twice, substituting the definition of density in terms of variable temperature using buoyancy, because this density variation itself is responsible for velocity. So this coefficient of volume expansion. So now integrating this equation twice and substituting all boundary conditions, this is the velocity profile, and this equals to 0. This equals to 0 when delta t square is neglected. So considering net mass flow rate in z direction, density variation, temperature variation, and delta t neglecting. So this is what rearrangement is done. So all after rearrangement, so we got, if we neglect the delta t square, so this is what we will get, net mass flow rate. Rearranging the terms, we will get, for this case, del p by del z equals to minus rho g. Substituting this in velocity profile, this is what velocity profile we will get, and this is the average velocity upward moving string, and using the dimensionless number, we will get a Grashof number, which is the ratio of buoyancy force to viscous force. Okay, if you have any questions, you can stay back in the class. Otherwise, you can join next class. We'll continue our discussion, and this was the last problem on heat transfer. From next class, we will be starting on mass transfer actually. Okay, thank you very much for this class.